No, lewanta.
Nie zerknąłem.
Tak pobieżnie zerknąłem.
The slide stack to be great.
Jest oczywiste. Nie znalazłem, żeby już powiedzieć.
Full name are infant.php.
Name first and last.
Yes.
Teorią miarową w takim sensie, to może i to tak. Może i to przeszło nawet.
Invitaciones. Diga Villauro. Cuento del tuyo. Pero ¿conoces a los?
Okay.
Buena coincidencia.
Bueno, bueno, no? No więc standardowo regulacji zrobił na L2 od G, takim małym L2.
To już w ogóle ciężko. To już nie ma
Nie, no ale chcesz standardowe takie rozumowanie przeprowadzić.
Son similares, la
Similares, pero
Standardowe grup rozumowania to jest to, że masz ten flat standardowy i on ci robi
Sí, porque
dawać, że masz coś.
yo no sabía que había notado, pero
te dieron cuenta.
No na pewno
Se veía bien. Ahí
może
le pusieron la vaina.
sobie żyją. Ja muszę wiedzieć na temat pani. Nie znam, ale mogę się pójść zapytać.
You live?
¿Cancelaron el tuyo?
You pack your stuff and all? But the flight at 12 or 1?
To już, ja muszę pilnować czasu. 1 minute. Okay. So do I need to know anything? You wanted to say anything? Okay. So I don't even have to read it. That's good. Yeah, it's good. She didn't want it. You don't want to tell me. Who is in charge of the camera? No one?
Took care of it.
Oh, good, thanks. Should be
I only feel
Yeah.
Never been there.
Like the way we want to get
Come for the week.
En la escuela de traducción polaco.
Mieliśmy 2 razy mniejszy skład niż
read your group personality. Yeah, sure.
Dobrze, bo wygraliśmy więcej.
think this is the one point.
Yeah.
No pasamos, así que no hay problema, cualquiera que sea.
The most important people are here.
So when you want.
Will not there.
Recording is now. The recording has started.
Hello, everyone. Good morning. So it's time to start today's last session with Maria Isabel Cortez, who will talk about stabilized automorphism groups of odometers given by group actions.
Okay, so first, thanks for the invitation. It's my second time in Poland, but the first time in Warsaw. I really enjoy this place, and including the weather. So I love this. I grew up in a place like this. Okay, so I'm going to talk about some kind of algebraic invariant of group actions on counter set. I'm going to explain with the time, maybe with easy examples. I'm going to start with, try to contain everything here. And I have to say that this is a joint work with Vicente Urria. Vicente Urria is a master's student in my university in Chile. So what is the general idea here? So the general picture of the thing that I'm going to talk here. So when you have a group action on a counter set, you can associate some algebraic object to this action. So for example, something that already were defined here, you can associate the full group of the action, the topological full group of the action. There are other algebraic objects that appear also for group action on the counter set, like the dimension group, the reduced dimension group. And some things that I'm going to introduce today also, like the automorphism group, the stabilized automorphism group, and many other objects. So when we have this algebraic object associated to these actions, the question that people in dynamics ask, because I'm from the dynamical system community, is, okay, try to identify the dynamical properties of the action that can be read from this object. So how can you characterize that two systems have isomorphic algebraic objects? You try to find some dynamical property for that. And so, for example, I'm going to talk later about this kind of things, but a typical example is the following. There is a classification of free CD actions on the counter set given by Giordano, Matui, Putnam, and Scow in 2010, when they proved two actions like this have isomorphic reduced dimension groups, if and only if they are topological orbit equivalent. So this is a way to describe this algebraic object in a dynamical way. And in general, when people start to think of these problems, they start to think first with C actions. So this was the case, for example, with this problem. They start to think of C actions, and then people try to generalize this to other group actions. And the idea here to generalize is not just to make a generalization because you want to generalize, but the thing what happened when you understand what happened with more general group actions, you have a better picture of the phenomena. So when you study just C action, you are seeing the phenomena through a little window. And then when you see this, when you understand the phenomena for more general group action, you understand better the dynamical phenomena behind. So this is the general idea about what I'm going to tell you today. And I'm going to focus in these two algebraic invariants, topological full groups, mainly on stabilized automorphism groups. And what I'm going to try to tell you today is something related to this kind of problem, something which is known for C action, try to understand what happened for more general group actions. And I'm going to tell you something for a very simple, without being trivial, family of group actions on the counter set. So I'm going to start defining the family of group actions on the counter set that I'm going to use in order to study this kind of problem. Okay, so in general, here I'm going to deal with counter systems, which are our group actions on the counter set. So I'm going to denote this always like this. So triple X alpha G, where X will be a counter set. G, a discrete group, most of the time it will be countable. Alpha will be an action of the group G on X by homeomorphism. And usually I'm going to write the action of the element G on X like alpha to the G of X or GX. And One of the most important objects here, or in dynamics in general, are the orbits. And the orbit of an element of the phase space, of an element X in the phase space, will be just what you get when you apply the action of the group on the element. So this is the kind of things that will appear here. So I'm going to start introducing some representations of this, we could say the simplest examples of actions on the counter set. And these are the minimal equicontinuous actions. So I'm going to start defining this in the following way. So suppose that you have a countable group G, and then suppose that you have a decreasing sequence gamma n of finite index subgroups of G. So for example, you can take G equal to Z and gamma n equal to 2 to the n Z, something like that. So we have this relation, gamma n plus 1 is contained in gamma n, and the index of every gamma n is finite. We are not asking here that the gamma n are normal, they are just finite index subgroups. So when you have this, there is a natural function, because you have this contention, gamma n plus 1 contained in gamma n. You have a subjective function from the quotient of G gamma n plus 1 to G gamma n, and the only thing that this function does is sending the coset G gamma n plus 1 to the coset G gamma n. This is the function that you get because of thanks to this relation. And when you have this, you can define an inverse limit. So you can take the set X of all the sequence in the product of the G, of the quotient G gamma n, that satisfies this property, the property that the image, but the function to n of the coordinate n plus 1 is equal to the coordinate xn. So this is the inverse limit. And this is that we call this space X, that we call this space X a sub-odometer. Then I'm going to explain why a sub-odometer and not an odometer. And what can we say about this set? Maybe you already know, but this is a counter set. If you endow this set with the, if set G gamma n, you endow each set G gamma n with the discrete topology and then the product with the product topology, we induce topology. This space X is a counter space. And also the topology is induced by this metric, so the typical metric. So you take two sequences and you say that they are at distance 1/2 to the k, if k is the first coordinate with these two sequences differ. So this is the typical metric in this kind of spaces. And here we have a natural action of the group G. So where is the action of the group G on X? Just given by left multiplication. So here you get an action of G on this space of sequences. And now this counter set with this action is a dynamical system that we also call a sub-odometer. So the sub-odometer generated by this sequence of finite index of groups.
It is always a counter set or M choice.
It depends. This is a counter set if the contention, if the sequence of subgroups doesn't stabilize. Because if it's stabilized, you get something finite. So here I'm assuming that the contention is strict.
The intersection of
Exactly. Maybe the intersection is not trivial. Maybe the intersection is not trivial, but what you need in order to get a counter set is that it's not stabilized. Okay, so there is another representation of these systems, and this is given by actions on trees. So for example, if you have a sub-odometer generated by a sequence of finite index of group gamma n, this can be represented, or this is conjugate to a group action on the boundary of a tree, an action induced by automorphism on the tree. And I think the first time that I saw this was in a paper of Grigorchuk, Nekrachevich, and Suchansky from 2000, but the explicit construction maybe is here in Gregor 2011. And the idea is the following. So if you have a subodometer, you can construct a tree in a very natural way. How you construct this tree? So for every n, the vertices of the level n are given by the set, the quotient set G gamma n. So it's so you start from a root, and then at level n, your set of vertices is just the quotient of G by gamma n. And then when you want to connect vertices, you do the following. You take a vertex on the level n. There are exactly index of gamma n plus 1 with respect to gamma n, edges starting at this vertex, and you connect this vertex G gamma n with H gamma n plus 1, if and only if H gamma n plus 1 is contained in G gamma n. And if you see that the set of infinite paths will give you the element of the subodometer, and the action here is given at each level by left multiplication of the group. So this is another way to think of these objects. Okay. So in general, this system has some very particular properties. So subodometers are always minimal. So that means that every orbit is dense in the space. They are equicontinuous. So it means the group act by isometry. And in general, every minimal equicontinuous system on the Cantor set will be conjugate to a subodometer. So this is a way to represent minimal equicontinuous on the Cantor set. All these systems look like this. And inside this family, there is a more particular family, and this is the family of the group rotations. And the group rotation, they can be described like a subodometers given by sequence of normal finite index groups. So when you define a subodometer given by a sequence of normal finite index groups, you get a group structure on the space X, and this is what we call an odometer. So when there is a group structure there, we call an odometer. And in general, what can you say when you have an odometer? So the space X is a compact group. You can see the group G as a dense group of X when the intersection of the gamma n is trivial, for example. And conversely, if you get any metrizable totally disconnected compact group that contain G as a dense group, and you see the action of G on K by left multiplication, this will be conjugate to an odometer, to a free odometer. So these are the ways to represent that kind of dynamical system. And for example, if the group G is abelian, you don't differentiate between subodometers and odometers, everything is the same. And the other thing that you can check, is not difficult to check this, every subodometer will be a factor of an odometer. Why? Because if you have a sequence of finite index group gamma n, to any gamma n, you can associate the curve, which is just the intersection of all the conjugate. This is a normal finite index group, and if you define the odometer generated by this sequence of normal finite index group, this will be an odometer, which is an extension of the subodometer. And in fact, it coincides with the Ellis semigroup, if you are familiar with this object. Okay, so this is the class of group actions on the Cantor set that I'm going to deal today, to try to see how, or what can we say about the algebraic invariance? How the algebraic invariant behave or different is the behavior when you go from C action to other kind of actions. So for that, I'm going to go to the first algebraic invariant. It was already introduced here, but I'm going to repeat the definition just to show you the complete picture here. So we are going to go to see what is the topological full group of a system and the relation with dynamics of this object. So again, suppose that we have a Cantor system, X alpha G. The full group that it was defined here, but the full group of this system is just the subgroup of the homeomorphism of X with the property that for every X in the phase space, there exists some element G in the group, such that when I evaluate F on X, it's just applying the action of G on X. So, or maybe you can think of these objects as those like the homeomorphisms where the orbit by these homeomorphisms are contained in the orbit of the action. And the topological full groups is the subgroup of the elements in the full group. Which are in some sense, there is some, the element G that you use to evaluate Fx like G, the action of G on X, this element G is constant in a neighborhood of X. And how can we say this? For example, you can say this saying that in the topological full group, you have all the elements of the full group for which there exists a closed partition of X. And for every element of the closed partitions, an element of the group G, such that the restriction of F on this, of an atom of this closed partition is just the action of the element of the group corresponding to this atom of the partition. So this is the topological full group that was already introduced here. And these two objects, these two algebraic objects are related to some dynamical properties. And I'm going to define these properties and then I'm going to show you what is the relation. So these are related with two concepts, two ways to compare dynamical systems. And these ways to compare dynamical systems are topological orbit equivalent and continuous orbit equivalent. So if we have two Cantor systems, X alpha G and Y beta H, so the groups are not necessarily the same, we say that they are orbit equivalent. This is always topological or topological orbit equivalent if there exists an homeomorphism from X to Y, sending the orbit to the orbit. So every orbit of the first system to an orbit to the second system. And the systems are continuously orbit equivalent if they are orbit equivalent, but there is some continuity in the way how you send the orbit to the first system, to the orbit to the second system. And this continuity can be said in the following way. So you say that they are continuously orbit equivalent if for every X in the space X, and for every element G of the group G, there exists a neighborhood U of X and some M element 8 of the group 8, such that when you take any element Y from the neighborhood U and you apply the homeomorphism phi to the action of G on Y, you get the action of 8 on phi Y. There is some continuity there. Another way to think of this is like the function that goes to the group G product with X to the group 8 to the pair GX send 8, where 8 is such that phi of the action of GX is equal to 8 to phi X. This function is continuous. This is another way to think of that. So here we have two ways to compare dynamical system. We have these two algebraic objects that I defined before, and how they relate. They relate in the following way. So this theorem was shown first for C actions by Giordano Putman-Skau in 1999, and then by Kostya Medinet in 2011. And this theorem tells you the following. So okay. Suppose that you have a Cantor system with some conditions. It's something like that every orbit has at least 3 elements, and I don't remember, but something very few conditions you have to ask. Okay, under these conditions, you have the following. The full group is a complete invariant for the orbit equivalent of the system. And the topological full group is a complete invariant for the continuous orbit equivalence of the system. So what does it mean? Does it mean that two systems have isomorphic full group if and only if they are orbit equivalent? And two systems have isomorphic topological full group if and only if they are continuously orbit equivalent. This is a classical result. But now, for example, you can ask you, okay, we know this, but maybe we would like to understand in a deeper way what is the meaning of being continuous orbit equivalent? What can we say about continuous orbit equivalence? And for that, we can think of what does it mean for C actions being continuously orbit equivalent? So what do we know about continuous orbit equivalence for C actions? This was already mentioned here in the conference, but for example, for C actions, we know that two C actions are continuously orbit equivalent if and only if they are flip conjugate. So what does it mean that they are flip conjugate? That one system is conjugate to the other one or to the inverse of the other one. So continuously orbit equivalent for C actions is very rigid. And then another way to write the flip conjugacy is the following. It's saying that the two systems are isomorphic. And what is an isomorphism of dynamical system that was also already mentioned here before? The systems are isomorphic if there exists an isomorphism between the acting groups. In this case, an isomorphism between Z and Z. We don't have too many options, so it's the identity or minus the identity that commute with the actions. So for C actions, these three things are equivalent. So in order to try to understand what is the meaning of continuously orbit equivalence for other group actions, you can think, for example, and I remember we start to think of this question with Kostya Medinet many years ago, and we were trying to understand what is the meaning of continuous orbit equivalence for this very simple class of Cantor system, for the minimal equicontinuous Cantor system. And the expectation that we had was to try to show that continuous orbit equivalence, in fact, is equivalent of being isomorphic. So we were expecting to show that two subodometers are continuously orbit equivalent if and only if they are isomorphic, because we knew that for C actions, this is the case. But in fact, this is false. And the thing that you get is the following. This is something with Kostya Medinet from 2016. What happened when you work with other groups beyond Z is the following. Suppose that you have two free subodometers. Here the acting groups are finally generated. Then the following things are equivalent. So the subodometers are continuously orbit equivalent. We already know that this is equivalent of again, sorry. This is equivalent to have isomorphic topological full group, but you can say something more dynamical. This is equivalent to be structurally isomorphic. And what is this? This is weaker. Structurally isomorphic is weaker than being isomorphic. And what is structurally isomorphic? In general, so a general way to say this is that two systems are structurally isomorphic if they have subsystems which are isomorphic, and the acting group on these subsystems are finite index group with the same index. This is the way to define this. More precisely, you say that these two systems are structurally isomorphic if there exist closed sets Cx contained in X, Cy contained in Y, and subgroups gamma of G, lambda of H, such that gamma and lambda have the same index with respect to G and H, respectively. The group gamma acts on the closed set Cx, and the group lambda acts on the closed set Ci. And when we compare these two actions, so the action given by the restriction of the action of gamma on Cx and the restriction of the action of lambda on Cy, we get isomorphic dynamical systems. So there exists an isomorphism between the groups gamma and lambda that commute, and an homeomorphism between the closed set that commute with the isomorphism of the group. And this is weaker than isomorphism. When you have something like this, you can't always extend this to an isomorphism of the entire group, as in the case of the actions. And there are many examples of.
Could you please say again what is the return times? What exactly? So we assume that Cx is exactly comes back onto Cx.
Yes. When I say return times, I'm just saying that the gamma. So if you take an x in Cx, and if gamma x is in Cx, this gamma is in the group gamma.
So it's possible that this element gamma is
Exactly. You have like a tower. Yeah. You have like a tower. Yeah, you have like a partition, so you can construct a partition using the translated copies of Cx. Yeah, this is what you get. And the thing is, when you see the base of these towers, given by the action of these return times, these two things are isomorphic. But if you can extend this isomorphism to the entire system, this is not always possible. For C action, this is possible, but here not. And there are examples, for example, the examples are always like this. For example, this is something for C2 odometers. So the way to construct these examples, which are continuously orbit equivalent, but not isomorphic, are more or less, follow more or less the same idea. So you take these two matrices with the same determinant. You define the group gamma n has all the elements of AN C2, HN like B, AN minus 1 C2. They are more or less the same, but one group is like, I don't know, distorted like this. And then you can show that there is an isomorphism between gamma 1 and H1 that send gamma n to Hn, and this will give you the homeomorphism between the closed set and the return times and the isomorphism system induced on these closed sets. But then when you want to see if they are isomorphic of dynamical systems, so the entire dynamical system, not just the induced dynamical system of the closed set, it will not going to be possible, because when you see this isomorphism between gamma 1 and H1, you can extend this to Z2. So this is more or less the idea. This is the way where you can produce examples of Z2 odometers, which are continuously orbit equivalent, but not isomorphic. And there are several examples like this in a paper from 2019 by Giordano, Putman, Scow, CD odometers and cohomology is the title, where they produce all the possible combinations. So CD odometers, which are orbit equivalent, but not continuously orbit equivalent, continuously orbit equivalent, but not isomorphic, isomorphic, but not conjugate. So you can do whatever you want. Okay. So again, this is what I said. So continuous orbit equivalent for C2 odometers is not equivalent to isomorphism. And this is in contrast to what happened for C odometers, for C actions. And for C actions, continuous orbit equivalent is equivalent to big isomorphic. So this is like the first examples that I wanted to show you in order to see why we can learn more when we generalize, not just for the act of generalize, if you want. And also another important, which is another result which is important, it's when you see this result about continuous orbit equivalence, you see that there is some rigidity between the groups that admit group actions that can be continuously orbit equivalent. So they have to be virtually isomorphic. They have to have a finite index of group which are finite isomorphic. This is the general proof of this is given by Xin Li in 2018 for the general case. So not any pair of groups admit continuously orbit equivalent actions. Okay, so now I'm going to go to the other invariant that I want to study. And the story here is, okay, I'm going to tell you something about the automorphism groups and stabilized automorphism group. And we start to see how the behavior of this object was for general group actions without knowing at the beginning that there was some relation with the topological full group. So we found a relation just by chance. And maybe the relation is just in the context of this very simple dynamical system. But anyway, there is something there. Okay, so I'm going to start with the definition of the automorphism group of a system. And the automorphism group of the system X alpha G is just the collection of homeomorphisms, which are conjugacy of the system with itself. So the homeomorphism F that commute with the action of the group G. This is the group of automorphisms. And this object have been studied in many contexts. Maybe the first one that I know is the context of the subshift of finite type for C action. So there are many works, maybe by Boyle, Lind, Rudolph, Hedlund, and where they show that this object is big in general. It's very big in the context of finite, the subshift of finite type for C action. And you can say things like this object always contain the free group with two generators, any finite group, and many results like this. And until now, it's not possible to differentiate all the full shift, for example, using their automorphism group. And in the context, for example, of minimal subshifts, this object, this group, is related with the complexity of the subshifts. So there are some results, for example, saying things like if the subshift has low complexity, meaning that not too many words of length n for any n, so the automorphism group of the system is small. So it's something that contains the integers and maybe some little group. and trying to understand in a best way of trying to, because here, people working in chip of finite type, okay, they have dealt with this object and they found that it's very difficult to deal with this object. And having this in mind, Hartman, Banach, and Scott Schmieding define this object for C action, the automorphism, the stabilized automorphism group. And who do you define this? Okay, suppose that you have the system X alpha G. You define the stabilized automorphism group of this system as the union of the group of automorphism given by the restriction of the action to the finite index subgroups. For any finite index subgroup, you get the restriction of the action to the finite index subgroup, and you compute the automorphism group. You take the union of this, and you get the stabilized automorphism group. And this is a group because if you intersect two finite index subgroup, you get a finite index subgroup. This property will allow to show you that this is a group. This is, and this can be a huge group, but maybe not. And okay, and I said before, this was introduced by Hartman, Schmieding in the context of subshift of finite type given by Z actions in 2022. And some of the results which are known for this object are better than what is known for the group of automorphism. For example, Schmieding in 2022, he shows several things, but one of the things that he showed is that you can say that two full shifts, the full shift given by the alphabet with M letters and the full shift given by the by an alphabet of N letters, they have the same stabilized automorphism group, if only if the primes that appear in the decomposition of M and N are the same. So this is a complete classification of full shift given by stabilized automorphism group. This is in the context of Z actions. Then this definition that I show you for group action that was given by Villasalo in 2023. And later, some people started, like in the case of the automorphism group, some people started to think of this object in the case of minimal Z actions on the Cantor set with low complexity, like in the case of the automorphism group. And the first work in that direction was given by Jennifer Jones-Barrow, and she studied the stabilized automorphism group for odometers given by Z actions and topic subshift given by Z actions. And then in another work with Espinosa, Sebastián Espinosa, they show that if two minimal Z actions on the Cantor set, I don't remember if they need transitive or something like that, but anyway, two minimal Z actions on the Cantor set, if two minimal Z actions on the Cantor set have isomorphic stabilized automorphic group, then this implies that they have the same rational eigenvalues. And what is a rational eigenvalue? Rational eigenvalue there are many ways to define this, but one way is saying the following. So P, an integer P, is a rational eigenvalue if the finite system given by the rotation on the group C, the C model P, is a factor of the system. So in other words, if they have the same stabilized automorphism group, so they have the same finite system, the same finite factors. And again,
Excuse me. can you see what this condition of being belonging to SAT means in terms of action on the rooted tree? If you do this procedure, which you wrote on the left, can you do this? And can you understand what is SAG in these terms?
Yeah, I'm going to explain that. Yeah, you can do it. Yeah, you can do it. In fact, I can tell you but I can tell you later. But in fact, the stabilized automorphism group, you can describe this group like the union on n on the positive integers of the automorphic group of the restriction of gamma n on X. And what happened there? That the minimal component of these actions are the cylinder sets. So you have something like an automorphism given by the action of gamma n will be something that in the Clopen set acts as the group, but permute the Clopen set. So it's something like the automorphism group of a minimal component and with some permutation group. And you take a direct limit of this and you get the stabilized automorphism group. This is more or less the idea. Yeah. Okay, and this is in fact what we use because you can describe this. Okay, before I'm going to tell you a consequence of this result of Espinosa and Jennifer Jones-Barrow. For example, this result tells you immediately that for C odometers, the stabilized automorphism group is a complete invariant for the conjugacy class of C odometers. Why? Because C odometers are completely described by this. And then the question is, okay, what can we say about stabilized automorphism group for odometers given by other group actions? Can we say something similar or maybe something different? We don't know. And the thing that we can say is the following. So for that, first, I'm going to define the following. Remember that for an odometer, we define an odometer like a subodometer given by a decreasing sequence of normal finite index of group. So the phase space X is a group. So this group acts on itself by multiplication, left or right multiplication. So I'm going to put names to these actions. The action of X on itself by left multiplication will be Lx, and the action of X on itself by right multiplication will be node Rx. Okay. So with this in mind, what we can show is the following. Suppose that you have two odometers, one given by the action of the group G, the other one given by the action of a group H. Then the following things are equivalent. So their stabilized automorphism groups are isomorphic if and only if the topological full group of the actions on the group X on itself and the group Y on itself are isomorphic, the right and the left. And this is equivalent to the following, and this is similar to what we got for continuously orbit equivalent, but it's weaker. And this is equivalent to the following. This is equivalent to say that there exist Clopen subgroups. U1, a Clopen subgroup in X, U2, a Clopen subgroups in Y, which are isomorphic as topological groups and such that they have the same index with respect U1 with respect to X and U2 with respect to Y. So this is equivalent to say that the odometers have the same stabilized automorphism group. And if you remember the condition of being continuously orbit equivalent, this is weaker. So if two odometers are continuously orbit equivalent, we have an isomorphism of two induced subsystems, and you can show that this will produce you an isomorphism of this kind, but the converse is not true. So you can have isomorphism of Clauben subgroup like this, but the systems, the odometers can be completely different. And for example, some consequence of this.
Can I ask you a question?
Mhm.
Can you go back to the previous slide, please? For this definition of the stabilized group for the odometer, right? You had the union over all finite index subgroups. What if you just take the sequence that defines the odometer? Will you get the same thing?
Yeah, you get the same thing. This is what I told to Artem. I mean to show you this later, you get the same thing. This is the nice thing
Just a
here.
little faster than I
Yeah.
am. So.
No, but you get the same thing. Yeah, before to show that, maybe I'm going to show you some consequence of this. So the first thing is that if two odometers are continuously orbit equivalent, then they have isomorphic stabilized automorphism group. And this can be deduced from several ways. One way is to pick this equivalent way to say that two odometers are continuously orbit equivalent. This thing that tell you that there are isomorphic inducer systems that will produce you an isomorphism of Clauben subgroup as you want. Another way is to see the computation of the automorphism stabilized subgroup and realize that the full group is a dense group inside of the stabilized automorphism group. But in many ways, you can show that continuously orbit equivalence for odometers implies the same stabilized automorphism group. Another thing that implies the same stabilized automorphism group is the fact that being, for example, if two odometers, X and Y, are isomorphic as topological group, then they have the same stabilized automorphic group. Why? Because you take like U1 X and U2 Y. And this allows you to find examples to tell that having the same stabilized automorphism group is weaker than being continuously orbit equivalent. For example, there are examples of finally generated groups, H and G, where H is amenable, G is non-amenable, with the same for finite completion. And when you see this, you can see X and Y, X as an H odometer, Y as a G odometer with the same stabilized automorphism group, but they don't have nothing to do as dynamical system because one acting group is amenable and the other one is non-amenable. And this tells you more or less that the stabilized automorphism group in the context of odometers is something more related with the group, not with the action, not with the group, with the phase space, not with the acting group. And okay, this is what I told you. So there are odometers with the same, which are not continuously orbit equivalent, with the same stabilized automorphism group. And then other thing that we can say, other thing that you can show, what happens now if you assume that two odometers have the same stabilized automorphism group? You can show that there are many ways to explain this, but you can say the following: if two odometers have isomorphic stabilized automorphism group, the groups, here is Hn gamma n, the group that you obtain as the group generated by 1 over the indices of the group gamma n, and on the other side, the group Hn, are the same. And another way to say that is telling you that if you take the group generated by the value of the measures of the Clauben set, measure the only invariant probability measure here, which is the hard measure. If you take the group generated by the value of the measures on the Clauben set, these groups are the same.
On the right instead G.
Hn.
And does it mean just that sets of indices of finite index subgroup are the same? Because gamma n, what is this sequence of gamma n on the left and on the right?
Yeah. But you say any group of finite, yes. Yes, this is this is another way to say that. Okay. Okay, and what I wanted to say is that for C actions, this condition, when we see this condition for C odometers, this is equivalent to say that they have the same rational eigenvalue. So here you recover the result for C action, at least for the C odometers. And another thing that we can say from this classification of orbit equivalence given by Giordano, Matui, Putman, Scow from 2010, they prove in the case of odometers, or in general, in the case of uniquely ergodic minimal Cantor system, the group generated by the values of the measure on the Cloband set, this will give you the reduced dimension group. So this is an invariant for topological orbit equivalence. So for CD actions, for example, if H is CD and G is EM, this condition implies that the odometers are orbit equivalent. So in the case of CD odometers, so if H is CD and G is EM, for example, we have that continuous orbit equivalent implies the same automorphism, stabilized automorphism group, and the same stabilized automorphism group implies orbit equivalence. And with this, you recover the result for C action, because for C actions, continuous orbit equivalence and orbit equivalence is equivalent to conjugacy for C odometers. All these properties are equivalent for C odometers.
So yeah, if H and G are continuously orbit equivalent, then D, the rank of those groups is the same, D equals M. But this other implication, right, is the two automorphism groups are isomorphic. Does it mean that M and D are equal or not necessarily?
Okay, you can go to the other side. Even if, for example, this is, I don't know if this is your question. For example, suppose that you take Hg equal to Z2. So you can find C2 odometers which are orbit equivalent without having the same stabilized automorphic group. And also you can find C2 odometer having the same stabilized automorphic group, but they are not continuously orbit equivalent.
My question is rather, if you have two systems, ZM and ZD odometers that have isomorphic stabilized automorphism groups, does it mean that ranks M and D are the same or not necessarily?
I don't know, but you can find completely different groups, acting groups, and with the same stabilized automorphic group. But it's the example that I showed before. But I don't know. Yeah, I don't know. Yeah, that's a good question. So, but what can we say is that this you can come back with these implicants. So for C2 odometers, for example, you have examples which are orbit equivalent, but not the same stabilized automorphic group, or things having the same stabilized automorphic group, but not continuously orbit equivalent. And here you get a difference from that we know for C actions. I don't know how much time okay, very quickly, I'm going to show you. This is something that you already asked, some of you. What is the idea to prove this? Okay, suppose that you have an odometer, maybe an odometer associated to this sequence of normal finite index group gamma n. The first thing that you can realize, this is not difficult to see, that the group of automorphism, in fact, is isomorphic to the odometer itself. In the case where you have an odometer, so something which is a group. If not, this is not true anymore. And then you can show exactly this, so that the group of stabilized automorphism, the stabilized automorphism group of the odometer can be computed like this way: the union over n of the automorphism group given by the action of gamma n. You can restrict to this union. And then something which is not difficult to see is that the minimal component of the action of gamma n are the cylinder sets of level n. And then you can show that if you pick an element F in the group of automorphism given by the action of gamma n, the thing that this element does is permute the minimal component, and on each minimal component, it coincides with the right multiplication by some element of X that will depend on the minimal component. So when you see this, you can show that in fact, this thing coincides with the topological full group of the action of the odometer on itself by the right. So here you have the first part. And the second part you can characterize having the same topological full group given by the right action of the odometer on itself in terms of this isomorphism between globe and subgroup having the same index. How can you do that? This is very similar what we did with Costia-Medinet for odometers, and the key step here is the thing that the isomorphism is spatially defined. When you use this, you get that this is equivalent to have an isomorphism between globe and set of the same index. So this is more or less the general idea, and I'm going to stop here. So thank you.
Questions?
Remark and question. So I was waiting for a long time the word profinite appear, and it appeared. So these groups involved are profinite groups.
Yes, these are profinite.
Totally disconnected. And these odometer actions, some people are called profinite actions. So there is a group of people that call these actions, just to be aware, profinite actions are sub-odometer actions or whatever. And now the question you mentioned, article by Kionke and Schenker or what? Do I correctly understand that they use branch groups to prove their result?
Yeah.
It's article dedicated to embedding in branch groups various type of groups, and I was not aware that I have this result that amenable, non-amenable group may have the same profinite completion.
And it's
So they use branch groups.
this result, how they show, okay, let me see where it is.
Next slide.
This one?
Yes.
Yeah, I don't know what they used to show that. Yeah. No, I don't know.
I think I'm aware of one article of 2023 and they use branch group. Only I was not aware that there is this suspicious for me result, but okay.
Maybe you don't believe it. Any more suspicions or questions? So let's fix it. We resume in 29 minutes, right? Oh, great. That's correct.
Paper was I think it's not.
But I think here
When do you have time?
it shows that they are very.
Check again. I don't remember. I think you gotta. I don't remember if you called and decided. I'm free all afternoon.
Huh?
Yeah, I'm free all afternoon. We got it.
Right now I go to